Hello and welcome. It is December 9th, 2025, and the eyes of the entire astronomical community are currently fixed on a single point in the constellation Leo, specifically near the star Regulus. We are tracking interstellar comet 3I Atlas, also designated as C2025N1, an object that has defied our expectations at almost every turn since its discovery. Tonight, we are diving deep into the latest data packet released just 24 hours ago by a joint task force from NASA and the European Space Agency. If you have been following the headlines, you might have seen reports suggesting this object was breaking apart or disintegrating under the intense solar radiation as it approaches perihelion. However, let's look closer at the data, because the reality is far more interesting and significantly more complex than those initial rumors suggested. The new imagery we have received, captured by the Hubble Space Telescope on December 8th, provides us with the highest resolution view of the comet's nucleus to date. Contrary to the fragmentation theories that were circulating on social media earlier this week, the nucleus of 3I Atlas remains remarkably intact. There is no evidence of the catastrophic structural failure we often see with comets that venture this close to the Sun. Instead, what we are seeing is a unified, solid body that is exhibiting a level of activity that can only be described as ferocious. The images show distinct, high-velocity jets of material erupting from the surface, creating a visible coma that has brightened significantly over the last 48 hours. This is not a dying rock, it is a waking giant. Before we get into the physics of this acceleration, if you want to stay updated on this developing story as 3I Atlas makes its closest approach, make sure you are subscribed to the channel. We will be covering the December 19th flyby live, and you won't want to miss that analysis. Now, let's address the movement of this object, because this is where the physics gets truly fascinating. Astronomers tracking the trajectory of 3I Atlas have detected a statistically significant anomaly in its orbit. Under normal circumstances, the motion of a celestial body like a comet is dictated almost entirely by gravity, the gravitational pull of the Sun and the planets. We can calculate these paths with extreme precision, predicting positions years in advance. However, 3I Atlas is deviating from that purely gravitational path. It is accelerating. It is moving faster than the gravity of the solar system alone should allow. This contradicts what we previously thought about the density and stability of this object. When we see non-gravitational acceleration in a comet, we are usually looking at the rocket effect. Imagine the comet nucleus not as a static rock, but as a chaotic engine. As the Sun heats the surface, volatile ices sublimate. They turn directly from solid to gas. If this sublimation were happening evenly across the entire surface, the forces would cancel out. But comets are rarely uniform. They have active regions, vents, and fissures where this gas escapes in concentrated, powerful jets. When a jet of gas shoots out in one direction, Newton's third law kicks in. For every action, there is an equal and opposite reaction. The comet is pushed in the opposite direction. This is exactly what we are seeing with 3I Atlas, but the scale of this thrust is puzzling. The acceleration suggests an incredibly high volume of mass loss, a rate of outgassing that is disproportionate to the estimated size of the nucleus. Here is the crucial detail that separates this event from a standard cometary outgassing. The acceleration vector is consistent with a specific type of chemical reactivity. We aren't just seeing water vapor pushing this thing along. The spectral analysis of the tail suggests a much heavier, more energetic exhaust plume. This behavior is linked to intense gas emissions, creating a reactive thrust effect that is far more potent than what we observe in local solar system comets. It is acting less like a tumbling iceberg and more like a volatile chemical canister that has been punctured. The comet is currently visible near Regulus, and as it races toward its closest approach to Earth on December 19th, when it will be just 270 million kilometers away, this non-gravitational acceleration is making precise orbital determination a minute-by-minute challenge. The navigation teams are having to constantly update their models to account for these unpredictable bursts of thrust. It is a dynamic situation. We are watching a visitor from another star system actively reacting to our sun, and the violence of that reaction is telling us something profound about what this object is made of. So, what does this actually mean for our understanding of the comet's composition? If water ice alone isn't enough to explain the intensity of this thrust, what else is burning off the surface of 3I Atlas? To answer that, we have to look beyond the movement and look at the molecules themselves. We need to analyze the smoke from this engine. This brings us to the work of the astrochemistry teams who have been pointing radio telescopes at this object, listening for the specific frequencies emitted by vibrating molecules. What they found wasn't just water. They found a chemical signature that is so strange, so unexpected, that it forces us to rethink the environment in which this comet formed. The acceleration is just the symptom. The cause is hidden in the spectral lines. We are dealing with a chemistry that is fundamentally alien to our local neighborhood. As we transition our focus from the physics of its movement to the chemistry of its atmosphere, keep in mind that this acceleration is the delivery mechanism. It is the force that is spreading these exotic molecules across our inner solar system, allowing us to sample the material of a distant, ancient world. The thrust we are observing is the result of a specific, volatile cocktail of ices sublimating into space. And the primary ingredient in that cocktail is not what anyone expected. It's not water, and it's not carbon dioxide. It is something far more complex, and its presence in these quantities is about to shake up the field of astrochemistry. We have established that 3I Atlas is an active, accelerating body with a solid nucleus, driven by a powerful reactive thrust. But the fuel for this thrust is the real story. In the next chapter, we are going to break down the findings from Martin Cordiner's team at NASA. We are going to look at the specific chemical compounds they detected using radio telescopes in Chile, and we are going to explain why a specific alcohol, methanol, is suddenly the most important molecule in astronomy. The numbers we are seeing are not just slightly off. They are statistically impossible for a solar system comet. This is the smoking gun that proves 3I Atlas is truly a stranger in a strange land. As we established in the previous analysis, the non-gravitational acceleration of 3I Atlas is being driven by a powerful reactive outgassing process. The comet is essentially a natural rocket, propelled by the violent sublimation of its own mass. But to understand why this engine is so powerful, we have to analyze the fuel. We have to look at the chemical composition of that gas envelope. This is where the story shifts from orbital mechanics to high-precision astrochemistry, and the results are nothing short of revolutionary. A research team led by astrochemist Martin Cordner from NASA has been conducting a detailed study of the comet's coma, the gas envelope surrounding the nucleus, using the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile. These radio telescopes are capable of detecting the faint, telltale signatures of molecules as they rotate and vibrate in the cold vacuum of space. Each molecule emits a specific frequency, a fingerprint that allows us to identify exactly what is floating around the comet. When Cordner's team processed the data from 3I Atlas, the results were unprecedented. They didn't just find a few anomalies, they found a chemical profile that stands in stark contrast to almost everything we know about comets formed within our own solar system. Let's look closer at the data regarding methanol. Methanol, or wood alcohol, is a simple organic molecule, but it is a critical building block in astrochemistry. In typical comets that originate from our Oort cloud or Kuiper belt, we expect to see methanol. It's not rare. However, the abundance is usually low. In solar system comets, methanol typically makes up about 1% to 2% of the total mass of evaporating substances. It is a minor constituent, overshadowed by water, carbon monoxide, and carbon dioxide. But with 3I Atlas, the sensors went off the charts. The data indicates that this interstellar visitor is releasing approximately 40 kilograms of methanol every single second. To put that in perspective, that is roughly the weight of a small adult human being ejected into space as pure alcohol every second. When we calculate the ratio, methanol accounts for a staggering 8% of the total mass of evaporating substances. This is 4 times higher than the concentration found in typical solar system comets. This 4 times higher concentration makes 3I Atlas a unique object. It is not just a dirty snowball, as we often call comets. It is a methanol factory. So, what does this actually mean? Why is this specific number, 8%, so disruptive? It implies that the ice chemistry of this comet is fundamentally different. It suggests that the environment where 3I Atlas formed was rich in carbon and oxygen in a way that our own solar nebula might not have been, or that the processing of these ices happened under very different conditions. We are looking at a sample of a chemical soup from a protoplanetary disk that might have been far more chemically active than our own. But the surprises didn't stop at methanol. The team also detected significant amounts of hydrogen cyanide, HCN. The emissions of hydrogen cyanide are amounting to between 0.25 and 0.5 kilograms per second. Now, half a kilogram per second might sound small compared to the 40 kilograms of methanol, but in the context of cometary science, this is massive. In ordinary comets, hydrogen cyanide is found only in trace amounts. It is a highly volatile, toxic substance that usually doesn't survive in these quantities or isn't produced at this rate. The presence of such high levels of HCN alongside the methanol paints a picture of a nucleus that is rich in nitrogen-bearing organics as well. This contradicts what we previously thought about the homogeneity of interstellar comets. We assumed they might be similar to ours, just from a different neighborhood. But 3I Atlas is showing us that different neighborhood might mean a completely different recipe for planetary formation. I want to pause here and ask you a question. If comets like this are common in the galaxy and they are carrying this much organic material, do you think they played a role in delivering the ingredients for life to Earth? Or is 3I Atlas a rare anomaly? Let me know your thoughts in the comments below. I read through them to see what theories you all are coming up with. Building on this chemical analysis, the team discovered something even more intriguing about where these molecules are coming from. It's not just that they are present, it's how they are being released. The analysis revealed a heterogeneous nucleus structure. This means the comet isn't a uniform mix of ingredients. The hydrogen cyanide appears to be originating directly from the nucleus itself, sublimating straight from the frozen ices on the surface. It is a primary product of the comet's composition. However, the methanol tells a different story. The data suggests that the methanol is partially formed in the gas dust envelope itself. It's not just boiling off the surface, it is being created in real time. As the comet releases dust and simpler gases, sunlight and chemical reactions within the coma, photochemical processes, are synthesizing methanol as the material expands into space. This implies a dynamic, reactive environment surrounding the nucleus. The comet is a mobile chemistry lab, actively synthesizing complex organic molecules as it travels. Here is the crucial detail. The disparity between the direct release of hydrogen cyanide and the distributed formation of methanol gives us a clue about the internal structure of the nucleus. It suggests layers. It suggests a history where different ices were trapped at different times or in different ways. The hydrogen cyanide is likely trapped deep within the water ice matrix, released only as the bulk ice sublimates. The methanol precursors, however, might be coating the dust grains that are being ejected, reacting only when exposed to the unshielded ultraviolet light of our sun. This complex interplay of direct sublimation and secondary photochemistry is what creates that massive 8% methanol signal. It is a signal that screams alien origin. It tells us that the ice we are looking at has been preserved in a deep freeze, likely for billions of years, protecting these volatile compounds until this very moment. We have the movement, and now we have the composition. We know it's accelerating due to gas release, and we know that gas is incredibly rich in methanol and hydrogen cyanide. But how does a comet acquire such a unique chemical fingerprint? How do you build a world that is 8% methanol? To understand that, we have to go back in time. We have to rewind the clock hundreds of millions of years, back to the birth of this object. In the next chapter, we are going to explore the internal factory of 3I Atlas. We will look at the formation hypothesis that explains this high metallicity and how liquid water, yes, liquid water, might have played a role in the deep past of this frozen wanderer. Building on the revelation of the 8% methanol concentration and the significant hydrogen cyanide emissions, we are forced to ask the question, how does a celestial body end up with such a specific and unusual chemical makeup? We know the what, methanol and HCN. Now we need to understand the how. The answer lies deep inside the comet, in what we might call its internal factory. The analysis of 3I Atlas has revealed a heterogeneous nucleus structure as we touched upon briefly. But the implications of this are profound. It means the comet is not a solid, uniform block of ice. Instead, it is likely a porous, layered object, a complex aggregate of ancient materials. The fact that hydrogen cyanide comes directly from the nucleus while methanol is partially formed in the coma gives us a window into the physical processes happening right now. But it also hints at the chemical processes that happened eons ago. Let's look closer at the data regarding the formation of these molecules. The leading hypothesis to explain the anomalously high methanol content involves a process that sounds almost counterintuitive for a frozen object, the presence of liquid water. Now, we aren't talking about surface lakes or rivers. We are talking about microscopic pockets of water within the porous layers of the comet's interior during its formation or shortly after. The hypothesis suggests that 3I Atlas formed in a protoplanetary disk with high metallicity. In astronomy, metallicity refers to any element heavier than hydrogen and helium. A high metallicity disk is rich in carbon, oxygen, nitrogen, and iron. As this comet was coalescing from the dust and gas of its parent star system, it gathered these heavy elements. The theory proposes that solar heat, or rather the heat from its parent star, melted the primordial ice. This water then penetrated the porous layers of the forming nucleus. Here is the crucial detail. When this liquid water seeped into the rock-ice matrix, it didn't just sit there. It reacted. The water encountered iron-containing minerals within the dust grains. This interaction, a form of aqueous alteration, triggered chemical reactions. Specifically, the reaction between water, carbon-rich ices, and iron minerals can catalyze the production of methanol. It's a natural chemical synthesis happening in the dark, warm interior of a forming comet. So, what does this actually mean? It means that the methanol we are seeing spew into space today was likely brewed inside the comet billions of years ago. It was produced by a warm, wet phase in the comet's early history, then flash-frozen as the object was ejected from its solar system and flung into the interstellar void. The comet is essentially a time capsule containing the chemical products of that ancient alien environment. This internal factory model explains why the concentration is so high. If the methanol were just collected from the ambient gas of the nebula, we would expect levels similar to our own comets. But if it was manufactured internally through these water-iron reactions, the concentration could build up significantly before the freezing occurred. The 8% figure is a testament to the efficiency of this internal chemical reactor. Furthermore, the presence of hydrogen cyanide adds another layer to this picture. HCN is a precursor molecule. It reacts readily to form more complex structures. Its presence in the nucleus, surviving in such quantities, suggests that while some processing occurred, creating the methanol, the comet didn't get too hot. If it had been cooked too thoroughly, the volatile HCN would have been destroyed or converted entirely into other compounds. This implies a delicate balance. Enough heat to melt ice and drive methanol synthesis, but not enough to wipe out the volatile precursors. It is a Goldilocks scenario of cometary chemistry. This contradicts what we previously thought about interstellar comets being pristine, unprocessed chunks of ice. 3I Atlas shows signs of processing. It shows signs of a complex geological and chemical history. It is not just a piece of debris, it is a processed artifact. The active sublimation we are seeing now, the reactive thrust discussed in the first chapter, is the unlocking of this factory. As the comet approaches our sun, the heat is penetrating those outer layers. The ancient ice, frozen for eons, is turning to gas. The pressure builds up in the porous structure until it bursts out, carrying the methanol and hydrogen cyanide with it. The photochemical processes in the coma that generate additional methanol are just the final step in a manufacturing line that started in another star system. This connects to the idea of the comet's journey. We have a body that was heated, processed, and then frozen. But for how long? And what happened in the intervening years? The high concentration of volatiles tells us something else very specific about its travel history. It tells us that this object hasn't been near a star in a very, very long time. If it had passed close to other stars on its journey to us, these volatiles would have boiled off long ago. In the next chapter, A Frozen History, we are going to explore the timeline of 3I Atlas. We will look at the evidence that suggests this body has been drifting in the deep freeze of interstellar space for hundreds of millions of years, untouched by stellar radiation until it entered our solar system. We will discuss what this isolation means for the preservation of the material inside, and why 3I Atlas might be one of the oldest, most pristine samples of alien chemistry we have ever encountered. We have explored the mechanics of the comet's acceleration and the complex internal factory that produced its unique chemical signature. But to fully appreciate the significance of 3I Atlas, we must understand the sheer scale of its journey. The chemical data we have discussed, specifically the retention of such high volumes of volatile methanol and hydrogen cyanide, tells a story of profound isolation. This is the focus of our fourth chapter, the frozen history of this interstellar wanderer. The anomalously high methanol content indicates the comet formed in a protoplanetary disk with high metallicity, as we established. But the preservation of that methanol is equally important. Volatiles like methanol and hydrogen cyanide are incredibly sensitive to heat. In the vacuum of space, they sublimate at very low temperatures. If 3I Atlas had spent any significant time in the inner regions of a star system, or if it had passed close to other stars during its journey across the galaxy, these chemical stockpiles would have been depleted. We would see a dry comet, a rocky husk, with only trace amounts of gas remaining. Instead, we see the opposite. We see a bursting, overpressurized reservoir of volatiles. This leads astronomers to a staggering conclusion. Active sublimation began at a great distance from the Sun, indicating the body hasn't been heated by stellar radiation for hundreds of millions of years after leaving its home system. Let's look closer at the data regarding this timeline. The turn-on point, the distance at which the comet started becoming active, was unusually far out. 3I Atlas began showing signs of activity while it was still deep in the outer solar system, far beyond the orbit of Mars. This sensitivity suggests that its surface has been in a state of deep, absolute thermal equilibrium with the cosmic background radiation, about 3 Kelvin for an aeon. It has not felt the warmth of a star since it was ejected from its birth cluster. This contradicts what we previously thought about the density of interstellar traffic. It suggests that 3I Atlas has traveled through the void without encountering significant gravitational or thermal disruption. It has been a ghost drifting through the dark, preserving its cargo of ices in a pristine state. So, what does this actually mean for the material inside? It means that we are looking at a time capsule that has been sealed perfectly. The formation hypothesis we discussed, where water reacted with iron minerals to create methanol, happened shortly after the comet formed. Then, some gravitational event, perhaps a close encounter with a giant planet in that alien system, kicked the comet out. From that moment on, the chemical clock stopped. The reactions froze. The methanol was locked in the ice matrix. The hydrogen cyanide was trapped. For hundreds of millions of years, possibly billions, it drifted. The universe changed around it. Stars were born and died. But inside the nucleus of 3I Atlas, nothing changed. It remained a perfect snapshot of that ancient protoplanetary disk. Here is the crucial detail. Because it hasn't been heated, the structure of the ice is likely amorphous rather than crystalline. Amorphous ice is like a liquid that has been frozen so instantly that the water molecules didn't have time to arrange themselves into a crystal lattice. It is a chaotic, glass-like form of ice that can trap gases much more efficiently than the crystalline ice we find on Earth. When amorphous ice warms up and crystallizes, which is happening right now as it approaches our Sun, it releases those trapped gases in sudden explosive bursts. This phase transition explains the anomalous acceleration and the reactive thrust we observed in Chapter 1. The comet isn't just melting, its microscopic structure is rearranging itself, expelling the ancient volatiles that have been trapped since the dawn of its creation. This deep freeze has another implication, one that bridges the gap between astronomy and biology. If organic molecules like methanol and hydrogen cyanide can be preserved for hundreds of millions of years, what else could be in there? We know that these molecules are the precursors to life. If they are shielded from cosmic radiation by the outer layers of the comet and kept at near absolute zero, complex organic structures could theoretically survive the interstellar journey intact. The fact that the comet hasn't been heated for hundreds of millions of years means that frozen organic molecules and even microorganisms from the time of formation in a distant planetary system could have been preserved inside its icy nucleus. This is not to say there is life on 3I Atlas, but rather that the conditions for preserving the chemical blueprints of life are far better than we assumed. The comet is a cryogenic freezer moving between the stars. This connects to the ultimate question of our place in the universe. If 3I Atlas is a standard example of an interstellar comet, then the galaxy is filled with these cryogenic arcs, carrying the seeds of chemistry from one system to another. It changes our view of the galaxy from a collection of isolated islands to a connected archipelago where material and perhaps potential is constantly being exchanged.